exploration panel involving a new space and non-space players. And this is the organized session by JAXA. And first, I would like to introduce you with the objectives of this panel. And then after that, I will introduce the panelists for this session. So the background and objectives of this session is in situ resource utilization will be one of the most critical key technologies for sustainable space exploration because this could significantly reduce the cost of space exploration. Therefore, ISRU is the main theme in the latest architecture study in the International Space Exploration Coordination Group, ISECG. Because the ISRU is very relevant to the technologies on the ground, such as excavation, roving, drilling, resource prospecting, power generation, soil processing, electrolysis, liquefaction, etc., etc. New space agencies, new space entities, and non-space entities will have opportunities to participate by their own technologies. Also, ISRU could enable commercial business opportunities by basically selling fuel in space. In this forum, we will discuss how ISRU will benefit the overall mission and architecture, what is a challenge for ISRU, how we can overcome the challenges, what business opportunities can be foreseen. And I would like to introduce the panelists. First, you can see Dr. Alexander MacDonald. Dr. MacDonald is the chief economist at NASA. He was previously the senior economic advisor in the office of the administrator and was founding program executive of NASA's emerging space office within the office of the chief technologist. He's the author and the editor of a number of NASA reports. And he's also a former executive staff specialist on the commercial space at NASA JPL, a former research faculty member at the Carnegie Mellon, and has worked for the university's Space Research Association while at NASA Ames, where he worked on a small satellite mission designs and served as the center's first research economist. He received an undergraduate degree in economics from Queen's University in Canada, his master's degree in economics from the University of British Columbia, and was a Calderon scholar at the University of Oxford, where he obtained his doctorate on the long-run economic history of American space exploration. He was also an inaugural TED Senior Fellow and received the AIAA History Manuscript of the Year Award in 2016. And next to Dr. MacDonald is Mr. Takeshi Hakamada. He's a founder and CEO of iSpace. Mr. Hakamada received his master's degree in aerospace engineering from Georgia Tech. Enchanted by Star Wars movies at a young age, the dawn of the new commercial space industry, and the success of non-governmental entities like the Ansari X Prize drew his attention and curiosity. Takeshi chose to enter the consulting industry after graduation, where he had developed team management skills and led multiple successful cost reduction projects. Since 2010, he has led Team Hakuto, competing for the Google Lunar X Prize. And in 2014, he contributed to meetings initiated by the Ministry of State of Japan to discuss the new space industry. Next to Mr. Hakamada is Dr. George Sowers. Dr. Sowers is a professor of practice at the Colorado School of Mines, supporting the world's first and only graduate program in space resources. Before joining CSM, he spent 30 years in space transportation industry working for Martin Marietta, Lockheed Martin, and the United Launch Alliance. He was the chief systems engineer for the development of the Atlas V rocket and led the effort to human rate the Atlas V for the launch of Boeing's Starliner spacecraft. In 2017, he retired from his position as vice president and chief scientist at ULA, where his team developed an architecture for fully reusable in-space stages fueled by propellant mined, refined, and distributed in space. Dr. Sowers holds a Bachelor of Science degree in physics from Georgia Tech and a PhD in physics from the University of Colorado. Dr. Sawas is a fellow of AIAA. And next is Mr. Naoki Sato. Mr. Sato received his Bachelor of Science in degree in Aeronautics Engineering from Kyushu University in Japan, and received the Master of Science degree in Applied Engineering, also from Kyushu University. Then he entered the National Space Development Agency of Japan, that's the predecessor of JAXA. Since 1990, he had been involved in the International Space Station program for about 16 years. After that, he started to work in the International Space Exploration Program formulation up to now. He's the current ISECG chair since April 2018. He also is the director of the Space Exploration Systems Technology Unit of JAXA Space Exploration Center since 2018. With that, we would like to have Sato-san's presentation. And if the presentation is ready, let's start on the first topic, which is the international exploration scenario and ISRU benefit. Mr. Sato.
Thank you very much. Okay. Chat is ready. So today I'm wearing two hats, which is ISECG, and another hat is JAXA. First of all, I'd like to explain the ISECG and the main products of the GR, the Global Exploration Roadmap. So next chart, please. Next chart. Could you go? Thank you. Okay, so I hope that many of you knows about the ISECG, but just in case, I'd like to talk a little bit about the ISECG and Global Exploration Roadmap. So ISECG is a non-political and non-binding coordination forum by 19 space agency and or office. We are talking about the common interests and common objectives or common goals of the space exploration, and also the common scenario and the common architecture. And this is 19 participating agency in ISECG. If your agency is not in this list, and if you are going to want to participate in the ISECG, please contact me. This month is the discount period. So, okay, this is the ISECG mission scenario. So we have ultimate goal of the human Mars mission, but in the next decade, in the 2020s, we are focusing on the moon exploration, starting from the Lunar orbit mission, constructing the gateway, and in around 2030 time frame, we are going to go to the lunar surface through the gateway in this scenario. But currently, usually the things tends to go to the right, but recently the things unusually or fortunately things are going to the left. Of course, it's Artemis project by NASA. So currently we are discussing about the human landing mission, first human landing mission in the 21st century in the 2024 time frame. So all things is going to the left. And also you can see the several resource prospecting missions in the dark gray lunar surface area. But you don't see the actual ISRU utilization in this scenario. But recently, ISECG started the discussion about how the ISRU can be utilized in this scenario. So current status on the ISRU at the ISECG. We have been working together about the understanding of the potential utilization of the lunar polar volatiles. And also, we have identified the ISRU as one of the critical technology for the sustainable international space exploration. And we are assessing the gap between the ISRU technology needed and the current status. So again, we have started the work to incorporate the ISRU into the overall scenario and architecture, as well as the NASA's Artemis program. So that's all for the ISECG and GR and ISRU. So from now, I'd like to talk about a little bit more concrete idea from JAXA. So this chart shows the ISRU concept for the sustainable lunar exploration. So first of all, we are going to transfer the some reusable lunar lander and also the fuel plant and expose a hopper. So after that, the fuel plant will be located in the South Pole area, and this plant will produce enough propellant for the reusable lunar lander and also the exposed hopper. The hopper, the idea is to go to the exploration area far from the South Pole, so that we can explore the many diverse area on the lunar surface. And for this mission, we need some fuel. Around 37 tons for the reusable lunar lander, and also around 20 tons for the exposed hopper. So we need around 57 tons for the one human lunar surface mission. So we need to produce this amount of the fuel at the fuel plant. This chart shows the CONOPS of this ISRU plant. So first we need to excavate the regolith, and also we need some regolith collection or regolith transportation systems. And also we need a water electrolysis system, liquefaction system, and storage system. And also we need a power system to run these systems. So the problem is how big this ISRU plant. And we roughly calculated the system size. A little busy chart, but in several cases for the water content rate, such as 0.1, 0.5, 1.0, and 10%, and calculated the overall mass and the overall power needed. Then this chart shows the comparison chart for the ISRU benefit. Horizontal axis is the number of human lunar surface mission, and vertical axis is a mass to LEO, which is, I think, almost corresponding to the overall cost. So as you can see here, the no ISRU case, the mass is increasing with the number of the human lunar surface mission, and the slope is relatively steep. But if we are going to use ISRU case, we need some initial cost, as you can see here, but the slope is relatively moderate. So then we have some cross point, such as 4 times or 5 times or 7 times, like that. But anyway, I think we can, if we are going to utilize the ISRU, we can benefit from that if we are going to do the sustainable human lunar exploration. And also we are going to use the technology from the ground companies, such as for the regolith extraction system, the backhaul on the ground system is, I think, the base of that system, and also the rigorous transportation system will be based on the carrier dump system on the ground, and also the hydrogen liquefaction system, and also liquid hydrogen tank will be based on the ground system. So that's all for my presentation.
Okay, thank you very much, Sato-san. I have a few questions about, well, but first of all, thank you very much for this ISRU perspective. And so you showed us this good assessment, but how realistic is this to realize what you have described?
Sorry, yes. Yes, I think we need to study this number in detail in future, but this number includes some conservative assumptions, such as the mass of each system and also the surface environment. So I think this number is already including some conservative assumptions. So I believe that this number could be changed in future in the detailed analysis, but it's already including the conservative assumptions. So I believe that this chart, this concept is feasible.
Okay, thank you very much. And have you, time is limited, but I have a couple questions to Dr. Sowers and Dr. McDonald. To Dr. Sowers, I understand that Colorado School of Mines has a similar study or assessment. And what do you think of this JAXA's ISRU plan?
I like what I see. I would probably be a little bit more aggressive than what JAXA has been, but I tend to take a more commercial approach to these kind of things.
Okay.
And I think the story is even better than what's being shown here.
Okay, that's very promising. And I have a question to Dr. McDonald. And also at NASA, I understand you have been conducting the long time on ISRU. And what is your thoughts on this utilization ISRU of the water resources for propellant for rockets?
Yeah, so it's a great question, and part of my job as an economist is to depress everybody, right? It's called the dismal science for a reason.
You're good at it, Alex.
Thank you, I try. And part of the reason is actually, I'm glad that you have this chart, because this actually shows you one of the challenges, right? Which is that even under some of these assumptions, it clearly doesn't make sense to use ISRU until you are guaranteed to have a number of missions that you need. I remember funding a study a number of years ago where another challenge came up, which was that they had done their economic model for how much money it would make, how much sense it made from an economic perspective, but they failed to account for the cost of the substitute good. The substitute good, of course, is simply launching the propellant from Earth. Now, I know George's models kind of have a large market that does not relate to the lunar surface, right? But when you focus on lunar surface propellant markets for water, some of the models that we've seen where you're just fueling the ascent vehicle and you don't have a hopper and you're not fueling a full reusable lander, you might have needs of only 5 to 10 metric tons of fuel a year. And so we're still early phase in the architecture, deciding what the sizing of the landers is going to be, and it's still not clear yet the time frame in which ISRU makes sense. That said, ISRU in general, I think, is one of those fascinating examples of an economic narrative, right? It is a story we tell about the future related to how we think the economy should work and we want it to work, right? And it's a story we've been telling for over 150 years, right? Konstantin Tsiolkovsky has been talking about ISRU in the mid-19th century. The first book I have found that people talk about asteroid mining, for purposes of resources used in space, is in the 1870s in the US. And we still tell the story about living in the future and in space in large numbers. And if we live in space in the future in large numbers, there's no question that we are going to want to use the local resources. The challenge is, the reality of the budgets today. And so that's why currently NASA is taking an approach that focuses on first validating the models we have for lunar water ice, right? The Viper mission is absolutely critical. Being able to calibrate our models is absolutely important. Second is investing in early stage technologies. NASA's Space Technology Mission Directorate has an exciting new program called the Lunar Surface Innovation Initiatives. That is going to be the source of funding for the early stage technology development efforts, right? So NASA is aggressively pursuing what I would call supply side push efforts on ISRU, developing the technology, validating the models. We're still at the point where we're not quite sure when it makes sense to turn on from an architecture perspective. But of course, we're very optimistic in making serious investments in order to make sure that that day is sooner rather than later.
Okay, great. Thanks for the thoughts. And then at the Sato-san, at ISECG, tell us how you're proceeding with the ISRU assessment so far and in the future.
Yes, so I think the ISRU could be the game-changing for the future architecture. Even though, yeah, we need to answer to the Alex's question, but I think there is big feasibility or chance to utilize the ISRU. So we are going to integrate the ISRU and also the science aspect and also the Mars forward aspect into the ISECG architecture and the scenario.
Okay, great, thanks. Well, let's move on to the next topic, which is the second one, challenge of ISRU and solution. And we would like to have a presentation from Dr. Sowers.
Right, thank you. Before I dive in, I want to do a short plug for the world's first and only graduate program in space resources. Our program is fully online at the Colorado School of Mines, so you can attend from anywhere in the world. And in just our second year of offering this program, we have 75 graduate students, many of whom are in the room today. So since one of my privileges as a professor is I get to embarrass grad students from time to time, so stand up if you're in our program. All right, thank you. Only two, there's two back there. Okay. All right, very good. If you're interested in the program, find me after this. I'll be around all day tomorrow. So why are we so interested in space resources, and why is there such interest around the world? It's pretty simple. The resources available just in the inner solar system are nearly infinite compared to the resources on Earth. And if we can bring those resources within the economic sphere of humankind, then it will spur the next great economic revolution. It will create an era, a post-scarcity era, if you can imagine such a thing, and provide prosperity for people all over the world. A few examples: the power output of the sun is 10 trillion times the power consumption of human civilization. Just one large metallic asteroid like Psyche, which is out in the main asteroid belt. Actually, there's a NASA mission to that in the next decade. Contains enough metals to last human civilization for millions of years at current consumption rates. And then, of course, water's everywhere, and I'll talk more about water. So we know the resources are there. We can see the potential, but there are large technological and economic hurdles. The good news is that the terrestrial resource industries have long developed processes and well-proven processes for how you develop resources. This is a graph from the mining industry, and it has two dimensions. The vertical dimension represents increasing levels of geologic knowledge. So we have to do the prospecting of these resources. We have to characterize them, how big they are, their geotechnical properties, the extent, the richness, all of that kind of stuff. The horizontal dimension are all the other factors, mining and processing technologies, the economic factors, are there markets for these resources, and then of course what are the legal, environmental, and other regulatory issues to be dealt with. If we gain confidence, high confidence in both those dimensions, then we can get to the lower right-hand side of the chart, which is what the mining industry calls a proven reserve. If you have a proven reserve, you can take that to the bank. You can monetize it. You can get a loan to go develop it because you know that it's there, how to extract it, and what you can sell it for. So let me focus on the example of water. To me, one of the great discoveries of planetary science over the last few decades is that there's water all over the place in the inner solar system. In particular, we believe now that there's water at the poles of the moon. This graphic shows both the North and South Pole, and the little green dots are surface ice indications of up to 30% by weight. And of course, if the ice is on the surface, that's the easiest to get. I'm from Colorado. I use the analogy of the first miners that came to Colorado were picking gold nuggets out of the streams. Surface ice are the gold nuggets of space resources. If they're on the surface, we can just basically pick them up. And of course, water is critical for sustainable exploration. It's essential for all life. It makes really good radiation shielding. And what I'm going to focus on is splitting it into hydrogen and oxygen for use as rocket propellant. I'm fond of saying that water is the oil of space. And if we have a source of propellant in space, that really changes everything. The reason for that is pretty simple. And I think everybody in this room, if you're at this conference, you know the rocket equation very well. And you know that the rocket equation, if you express it in terms of propellant mass as a function of delta V, is exponential. It increases at an ever-increasing rate. In the upper right-hand corner, that graph, the blue curve is the basic rocket equation for a sample rocket that I picked. If you can refuel the rocket, you can go from the blue curve to the orange curve. And essentially, if you have the ability to refuel over and over again, you break what's called the tyranny of the rocket equation. And that physics is also expressed in the economics. The lower right-hand graph, the bars represent the cost of moving a resource from Earth to a certain place. The blue bars are the cost launching from Earth with no refueling. The little green bars are the cost of propellant if you can mine it on the moon. And then the orange bars are the cost to move from Earth to a certain location if you can refuel en route using lunar propellant. And what you can see there is that the cost to fly from Earth to the surface of the moon can be cut by a factor of 3 by refueling with lunar propellant. The cost to go from Earth to the gateway can be cut by a factor of 2. So you can see the tremendous economic leverage that you can get by utilizing lunar propellant. And again, this is not on the surface. This is exporting that fuel into cislunar space. So how do you extract the ice and turn it into propellant? At the Colorado School of Mines, we've been looking at a number of different architecture options. This particular one utilizes reflected sunlight from crater rims into the cold, dark, permanently shadowed regions where the ice happens to be. This is our design concept for the ice extraction system. So sunlight comes in from the crater rims, reflects off that flat mirror, which we call the secondary optics, goes through a transparent top on that sort of cylinder-shaped collection tent, vaporizes or sublimates the ice on the surface or the near subsurface, which then is captured by that tent, moves into these little tanks on the outside where it refreezes, and then we trundle them off to a processing facility for electrolysis and conversion into propellant. I want to give a plug to NASA. They're supporting this work through the IAC program, so thank you for that. Another example in cislunar space is there's water in asteroids. Most C-type asteroids contain water that's chemically bound in the rocks. And again, by using concentrated sunlight, you can break those rocks apart and release the water vapor. This is a concept that was also created under NIAC by a small company called Transastra. But you basically put the entire asteroid in a bag and use the concentrated sunlight to release the water and collect it. Another example of space resources brings energy to bear. We talk about the space economy, but all economies are founded on a bedrock of consumers. And so we have to figure out how space brings value back to consumers. And so space solar power has the potential for unlimited, inexhaustible, completely green energy that could be available anywhere in the world, 24 hours a day, 7 days a week. This is a concept by my friend John Mankins, used to be a former NASA employee. And it's a massive object. It's a 2 gigawatt power plant that would be in geosynchronous orbit. It's 13 kilometers by 6 kilometers. It's an enormous object weighing in at around 10,000 metric tons. It's utterly unaffordable if we had to launch it from Earth. But if we can build it from lunar materials in a high Earth orbit, then the cost drops dramatically, it becomes affordable, we can close a business case, make money, and provide energy to Earth forever. So with that, I look forward to questions and discussions. Thanks.
All right, great. Thank you very much, Dr. Stowers. Yeah, those are all very exciting and interesting, and especially to me, the ice extraction system that you showed me, that looks very terrestrial and it looks pretty promising and exciting. But how much of existing terrestrial technologies are already applied to that system?
So one of the inspirations for that method of extracting ice is the terrestrial environmental remediation industry. So if you have contaminated soils on Earth, one way to clean the soils is to either dig them up and heat the soils to release the volatile materials, or do it in situ where you can drill boreholes and plant heaters and cook the soils that way. So this is a method to release volatiles from material without the cost and expense of excavation.
So it's a very matured system already, in a sense.
So I mean, the ideas are mature. I mean, implementing it on the surface of the moon is obviously not mature. We've got testing underway in our labs at Colorado School of Mines in our cryogenic vacuum chamber, where we're creating icy regolith samples and heating them from above, and computing sublimation rates and those sorts of things. What's not known is can you create enough production rate, if you can get the production rate high enough to close a business case. And that kind of depends on what we need to know from hopefully from NASA, which is where's the mother lode of ice, and what's how deep is it, and how much of it's on the surface, and all those other ideas. But of course, if you can't get the surface heating to work, then you can start drilling holes and doing it that way, or do what you guys have looked at, which is just the sort of the brute force method, which is just dig it up and cook it.
Okay, thank you. And I have a question to Hakamada-san on this one, if I may. I understand iSpace is also proceeding with space resource development together with the conventionally non-space industry. And concretely speaking, could you tell us about what kind of activities are you involved in this with the non-space industries, and at this time, what kind of outcome are you expecting?
Well, we are currently working with the several non-space companies for the Hack-to-R missions. One of the good example is we're going to utilize one of their technologies, solid-state battery, for future lunar exploration. Especially the place water exists would be polar area. It required the heat during the because it's a thermally severe environment. So using the solid state battery instead of liquid battery, we can keep providing heat and then power to extract water and then produce water on the polar area. And then also in the future, at the time we actually extract water and then produce propellant, we need relevant technology, a plant technology or the storage technology, which is not space technology at all. So we need to work with terrestrial players who have such a technology on the ground.
Okay, great. Thank you. Well, in the interest of time, I would like to proceed to the next topic, which is the excuse me, feasibility of commercialization of resources. And here, I would like to have a presentation from both Dr. McDonald and also Mr. Hakamada concerning the commercialization of the lunar resources and its potential possibilities. So it's already iSpace presentation is here, so Ms. Hakamada, please.
Thank you. Well, I'm Takeshi Hakamada, founder and CEO of iSpace. I'd like to introduce about what we are doing and what we are aiming to do in the future. First of all, we are first going to create transportation system to the lunar surface. Our concept is small, low cost, and high frequency because at the beginning of this stage, iteration of the mission is important. So we are going to provide transportation service for the government, space agency, or other commercial players to do technology demonstration iteratively. And we are currently developing lunar rover and the lunar lander. Our lander can carry about 30 kilograms payload. And then we are aiming to do missions several times per year in the future. And then, also we are developing lunar rover. This is the lightest lunar rover in the world, I believe. The mobility capability we have, the mass of the rover is just 4 kilograms for the mobility part. Of course, if we bring some payload as a sensor, the mass of the rover will be increased. But right now, we realize the mobility capability within that minimal mass. And then we're gonna bring these small rovers, multiple rovers at the same time on the lunar surface. And then we already initiated 2 technology demonstration missions we called Hack-to-R program. The first mission, we aim soft landing in 2021. And then second mission is 2023 with a rover. And then we are aiming to do surface exploration. And then we are working with commercial companies for this mission. We have 6 corporations working with us for this mission. JAL, NGK, Mitsui Sumitomo Insurance, Citizen, Suzuki, Sumitomo Corporation. These are non-space companies, but they are interested in working with us, contributing the technology development and also creating business case for future space market. And then also we are working with Draper to contribute for NASA's mission, where NASA recently announced commercial lunar payload service called CLIPS. And then we are selected one of 9 providers for this program with Draper. Draper is in charge of the prime contractor for the NASA. And then iSpace in charge of the lander design and then mission operation. And then General Atomics, they are in charge of the lander manufacturing in the United States. And then also we are working with spaceflight industry for the launch support. And then this is our vision videos. No audio. Supposed to have audio.
Only 20 years ago, this city didn't exist. It's the result of pioneers sending rovers, then discovering water. The hydrogen and oxygen separated from water becomes energy, creating the foundation for a fuel station. And with the fuel station came scheduled flights, followed by settlers. Soon, settlers required more diverse skills, attracting new specialists for construction, steel, communications, energy, transit, agriculture, medicine, and more. People travel from far and wide to see this new city. We call it Moon Valley. The moon is the new staging ground for your next level business. Expand our planet. Expand our future. iSpace.
So transportation is just a first step, and we have this very big vision. Our corporate vision is expand our planet, expand our future, which means we want to create a world where humans can live in space. And even though this is an ambitious vision, but we have logical step for its realization. We are going to start from the transportation, establish affordable and frequent transportation system to the lunar surface. And then we're going to do this, in 2020s. And then we're going to implement several missions per year and then keep sending multiple rovers and landers on the lunar surface. And then important thing is to obtain data on the lunar surface for the next step. That is, resource utilization. And then once we have enough data to identify water resources and the economical benefit to exploit water on the moon, we move to the second phase and then expose the economic value of the space resources and then create platform to utilize the resources. Especially the water is important resources for us. And then once we can create gas station on the moon or around the moon, we believe we can transform space transportation dramatically, and then we can promote more activities on the moon and in space to support architecture in space, and also to benefit to the life on the Earth as well through the infrastructure already built around the Earth, like a satellite. And then if we can initiate such a architecture, we believe we can approach to our vision to create a city on the moon and then create a big industry for all the players can benefit as a business. But one important thing is that we cannot do it by ourselves as an iSpace, and even the existing space players. We need to invite many of non-space players to create this big industry in the future. So key is how to get involved with terrestrial industry on the Earth. Once we create the world human can live in space or on the moon, every service or product related to human life have to be in space or on the moon. So not only just resources, but also the logistics, energy, power, telecommunication, health, food or consumables. We need such stuff on the moon as well. And that's it.
Okay, great. Thank you for a great presentation. And Dr. McDonald, I understand you don't have view charts, but if you could give us your thoughts on this feasibility of commercialization of the resources, I appreciate that.
I'm happy to. If I had to get charts, I would have to get them cleared by headquarters, and that's always another matter. So I mean, I love that video of Moon Valley. I think it's just so beautiful, and I really want to see a Miyazaki film, based in Moon Valley, because I think it's a great example of the economic narrative. I mean, that is the economic narrative that we are trying to establish and promote. And so what NASA is really trying to do now, obviously, is to create the basic foundations to begin that development. And we're doing it in at least 4 distinct areas. Number 1, obviously, Artemis. I think you might have heard about it a little bit this week. But this is a plan, obviously, to return to the moon in 2024, and then hopefully return annually for the indefinite future, provided we can continue to support that. That is the basic foundation for sustainable space activities, if we're able to do that. And of course, NASA is doing this in a way that is going to have the Gateway, another piece of sustainable activity in lunar orbit, and we're partnering with commercial companies for the development of the human landing system. So we're already leaning heavily into enabling commercial development, which will be able to feed forward ultimately to commercial development of space resources once they become economically accessible and economically valuable within the space ecosystem. Of course, the first thing that NASA did under the current administration related to lunar exploration was establish the CLPS program, Commercial Lunar Payload Services program. And this is a very serious commitment. This is about $200 million a year in the Science Mission Directorate. This is focused on both the development of the science payloads in the science community, but also on purchasing services from commercial lunar landers. So once again, the strategy for developing access to lunar surface that NASA is investing heavily in is relying heavily on commercial lunar landers. And obviously iSpace is partnered with Draper as part of the people who are in the CLPS program. And the opportunity is to keep doing new selections. There are 2 missions that are planned to go in 2021 at this time, but there's going to be another round of selection. So this is going to have a very high cadence of missions that are going to allow commercial companies, academic companies to be able to test the technologies, to conduct the science missions related to developing space resources. Third, NASA is also doing a dedicated science mission, the Viper mission, to validate the models that we have for lunar water ice presence at the poles. This is going to be a dedicated SMD mission that is going to be focused on conducting with a rover the types of analysis that will help to bound our models for how much water is present, where it is, that kind of activity. So it's a critical mission for actually validating the presence of the resources at the South Pole. And fourth, but not least of which, in terms of NASA initiatives for space resources, is the LSII program, which I mentioned earlier. And this is about a $15 million a year initiative, which is dedicated almost exclusively to ISRU technology development. And so when you combine all these things together, what you have is a suite of programs that is dedicated to establishing a sustainable presence at the moon. And NASA's investing, obviously, for things like the Artemis program, this is going to be totaling in the billions of dollars. This is a major investment that NASA and the US government is being prepared to make on this. But we're doing it in a way that is partnering with the commercial sector, that is partnering internationally. And so we're doing what we can to lay the foundation for a sustainable space economy based at the moon. Again, I'm an economic historian. I do believe a lot of this is going to take a lot longer than people realize, but that's okay. The great benefit of long-lived organizations like the International Astronautical Congress is that we tend to stay at this for many decades at a time. And it's going to take decades. But that is part of the journey to places like, whatever future habitation that we're going to have on the moon is going to look like. And we are moving aggressively and very seriously right now to lay that foundation.
Great. Thank you for your insight. So I have a few questions on this topic. The first one is to Hakamada-san. Yeah, thanks for the great presentation. And so for commercializing these resources utilization, I wanted to know if you could provide us with some specific price setting and then like a concrete customers perspectives. And if you could provide us any of the information about we'd appreciate that.
Well, regarding the pricing, we believe still it's kind of early to discuss the concrete number because the pricing depends on the cost at this moment, and then we have a still great uncertainty about what kind of the investment necessary to create propellant in the future. And then from the market side, of course, lower price is better always. So we have an incentive to reduce the investment at the beginning and then try to produce propellant or the resources more efficiently. So I believe that in order to that technology at the beginning to implement multiple technology demonstration on the lunar surface iteratively. Otherwise, it's hard to estimate proper number for the future settings, the future pricing for the resources.
Well, thank you very much. And Dr. Sowers, the same questions to you, especially in also this the price setting as well as the customers, the perspectives.
So in 2016, when I was chief scientist at United Launch Alliance, I stood up in front of a space mining conference and told them that I don't know nothing about mining in space, but I'm here to buy propellant. And I told the audience what I was willing to pay. On the surface of the moon, $500 a kilogram. In high Earth orbit, L1 type orbit, $1,000 a kilogram. And those prices were based on being able to lower the cost of a launch from Earth to any destination beyond low Earth orbit through refueling. Since I joined the Colorado School of Mines, we've been doing cost analysis on, what could we provide it for? And, we think those prices are achievable. And if they are achievable, then every launch company that launches beyond low Earth orbit would benefit from buying that propellant.
And that's a good comparison. If you base that the cost to launch, weight to a low Earth orbit, that's a very comparable number to start with. Thank you very much for your insight. And I have a question to Dr. McDonald about how to avoid this competition because the water, ice, and then also the sunlight. Those areas, they are limited. Those the areas that are rich in those resources, and so there's a possibility that it could be a very good competitive field, and in order to avoid that kind of thing, and then make it I would say very reasonable, healthy, competitive market. How do you achieve that? What would be something that you can tell us about how to achieve that?
Yeah, that's a good question. It's so good it might get me in trouble. So currently, the U.S. policy is essentially, one that says that, U.S. legislation has been passed, signed by the president, that says that if you mine it, the U.S. considers that you own that material. This is something that the U.S. considers to be within the bounds of the Outer Space Treaty because we're not appropriating any territory, and nor would any U.S. entity that was engaged with that. I do think that that is going to be important. You have to be able to have clear ownership of the material that you have. However, as long as there isn't appropriation of the territory around it, then multiple parties can be using the same territory, right? And I think that principle is also critical for basically international cooperation in space. I remember I actually went to the Johnson Presidential Library to read the initial negotiation notes that President Johnson's team had for the negotiation of the Outer Space Treaty. Because there's a certain narrative that says, well, they didn't really agree at a kind of presidential level with some of these ideas of the Outer Space Treaty, right? And when you read through the negotiation notes, it's very clear that they understood exactly what they were signing. Because President Johnson, in some of his announcements related to signing this treaty, said that he believed that we should be proceeding under a different era of cooperation in the future in space. That we shouldn't just port all of our old economic models, because whatever we do in space is going to propagate effectively, potentially, indefinitely, and infinitely. So we have to be very thoughtful about the way in which we structure our relations with each other as an economy. At the same time, we understand that you need to have certain levels of private property in order to be able to do exchanges. So for me, I think the way we deal with some of these issues, and this is just me speaking, this is not NASA, this is not the US federal government, I think we have to recognize that ownership of some of the extracted resources, once you have extracted them, is something that can be allowed under private property. However, we should not be setting up zones that are claimed by any country, zones that are claimed by only any one company, without that being something that is part of an international arrangement. I don't know exactly what that international arrangement looks like now, and I don't think we need to determine what that international arrangement looks like now. I think it's too early. But I think these types of thoughts, that we don't want to go into an era of competition. We want to think about structures that allow for private property with international cooperation and openness is the general vector that we should be thinking about.
Okay. Thank you very much. And yeah, those are very important thoughts that as we explore and then try to commercialize the resources utilization, yeah, we have to always keep that in mind. I have a question to Hakamada-san in a similar manner, but for the commercialization of lunar resources. We have, Dr. McDonald from NASA and JAXA folks here. And what kind of things do you expect from the space agencies, the governmental space agencies?
Well, at this moment, the commercial company like us is still small, and then we cannot do everything by ourselves. So we still need still work with government and the space agencies to create a new ecosystem in space. And then the CRIPS is, we think, that very important step for the working together, government and the commercial companies. The NASA procure the service, not run the service of the transportation, and then wherever the payload is, NASA want to deliver the payload on the lunar surface. And then we just provide the transportation service to them. And then because we have certain level of customers from NASA, we can more easily to invest our technologies and then set up the affordable transportation system. And that is very important for us to go to the next step to enlarge our system to be able to do space resource mining and utilization in the future.
Okay, great. Thank you. And I think we have a few minutes to spare, and if any audience has any questions, we'll be happy to take your questions. Any questions to anybody? Yes, please.
Thank you. One of the questions that I have is, I imagine that a lot of economics built around resource utilization on the moon are predicated on still having high launch costs on Earth. Will substantially lowering launch costs on Earth, if we get down to, let's say, $100 per kilogram or $1,000 per kilogram, does that ultimately, it makes it easier to go to the moon, but does it undermine the economic case?
Yeah,
Please,
I'll
please.
take it. It changes it. It doesn't undermine it, in my opinion, because some things get cheaper, right? The cost to establish a lunar mining operation depends on the cost to launch things from Earth to the surface of the moon. But eventually, it does erode a little bit, but, you're still faced with a rocket equation, right? That's not going away.
Yeah, and I would say it certainly can. And we have seen cases where, a business model seems to make sense, and then once you assume that you're, able to launch all this low-cost stuff, under certain circumstances it doesn't. But I also agree with George that, eventually, there are certain destinations in the solar system that are significantly far away, and eventually we're going to want to be able to source propellant locally. And so it's very contextual. It's very contextual to the technology that you have at the time, contextual to the demand you have at the time, contextual to the amount of certainty you have about your future demand, and all of these things. We're at a time where we don't have enough guaranteed certainty where we know that these cases close at the moment. However, we are aggressively investing in it. So there are absolutely cases where low-cost launch could eliminate the cases in certain circumstances. But we know that ultimately, to have a spacefaring civilization that expands throughout the cosmos, we're going to need to still do it.
Ultimately, if you have a commodity market for fuel in space, then it doesn't matter where the fuel comes from, right? It's just fuel. When you pull up to the gas pump, you don't know where that fuel came from. It could have come from Saudi Arabia. It could have come from Alaska. It could have come from Texas. You don't know. You don't care. And so, those costs set the commodity price, but, once we have a commodity market, the fuel can come from anywhere.
Great, thank you. Any questions from the audience, please?
Yeah, thanks. Thanks very much for the good discussion. There's obviously a lot of uses for water in the solar system, but you talked about propellant usage. One of the issues is, what is the purity of that rocket fuel that's going in there, the fuel in the oxidizer? Have any efforts been made to characterize how pure we can get it and get it sufficient, particularly in a microgravity environment, if you're using asteroidal resources versus the surface of a large body?
That's funny, Dan, because you know, if someone ever gave me that question, I would say, I don't know, you should talk to Dan Mazanek and see whether or not he knows. I know that the issue has come up repeatedly as to how do you qual it, right? So you say you've produced it, and you produced it at a autonomous base, right? What is your method of qualifying the use of this, especially if it's for something early stage in a NASA exploration architecture where your propellant is mission critical, right? And I think we've recognized the issue, but you know, I guess what you're telling me is that, you know, we haven't let any contracts out to Langley yet to figure it out, or Goddard.
Well, when you buy propellant on Earth, you buy it to a spec, right? So I would assume that you'd have a similar specification for propellant that came from anywhere. And then it's up to the supplier to make sure they meet the spec, and then you can have quality control to ensure it occurs.
But I do think what you're getting is quality control in a autonomous place that you don't live at is a new problem that we have not yet had to solve. And that is a real serious issue, and I think this is one of the many technical challenges that are solvable, but that we need to do the hard technical work to figure out how you're going to actually resolve it.
Right, great question and great answers. Actually, time flies, and we have to come to this closure. And in summary, just wanted to summarize the discussions, and thank you very much for fruitful discussions and the great presentations. Yeah, so this water purity is very important, and how we get that is very extremely important. So we can expect that efficient lunar exploration is highly possible by utilizing the water and ice resources on the lunar surface. But however, we all discussed, as we discussed, we need to understand the accurate quantity as well as the quality of the water, of the existing water on the lunar surface, as well as in what condition that water exists. And in order to utilize the resources on the moon, we need the technologies, as a lot of you mentioned, not only the ones that the current space industries have, but also the other various technologies that currently non-space industry already has. And we need to integrate these terrestrial technologies by having more private sectors participating in this effort. And of course, this will lead to this ecosystem that we all talked about. And it's possible to commercialize the utilization of lunar resources. However, we need to carefully assess the trend of the potential customers of the resources. And then also, we need to establish a legal framework in order to avoid the excessive competition. We need to make it a very healthy and competitive market. And last one is, in order to utilize realize this ecosystem, as Sato-san is currently the lead of the ISECG effort, we expect the efficient exploration scenario utilizing the resources on the moon will be established in the ISECG effort. And because this could be very controversial, we need to have a very close coordination among the partners, industrial partners, as well as the international partners. So I am very positive that ISECG needs to play a key role in establishing this reasonable scenario for exploration. And yeah, do you agree with this proposal or this summary? Appreciate that. Okay, so Sato-san, would you like to? Yes. Okay.
I got that.
Okay, he got the action. So thank you very much to accept another homework. So thank you very much for participating in this one, and thank you for the great questions. And I would like to finish this session now. Thank you very much. And please give another round of applause to the great panelists.